In this video, we're going to see improper integrals appear in a different way or in a different context. The infinite quantity might not actually appear in the expression. It might be something that's hidden more through the integrand. We're going to see how we work through this through some examples, and the approach is exactly the same that we took with limits to infinity, but we're just going to have to be a little bit careful about recognizing those infinite quantities when they're not as obvious. As a first example, let's evaluate the integral from 0 to 1 of 1 over root x. Now there's no obvious infinity here, or no obvious infinite quantity, until we sketch a graph. So it might not be obvious, but it is there. If we sketch the graph of 1 over root x, it goes through 1, 1, has an asymptote horizontally as x approaches infinity, but we're not interested in that this time. We are interested only in the interval from 0 to 1. But you'll notice as x approaches 0, we're going to be dividing by 0 without any cancellations, and so we're going to have a vertical asymptote in this graph. Well, that means that this 0 point here, the function is not defined there. And so that's what makes this an improper integral. So how do we get around that? Well, we take the same approach we did before, and instead of using 0 as our point, or our lower limit, we are going to carefully calculate the area up to some other point instead, where the area is finite. If we cut off this integral at some positive point A and go up to 1, this area is fine. Or we get a proper integral if we represent that using our integration notation. Then what we do as a follow-up is say, well, what if I push that a value closer and closer to 0? Remembering what we did before, we would have taken an area from some point, let's say here 2 for visualization, and then some point b, and then we would have let b go to infinity, asking what the area is underneath that. This time we're just going to let a approach 0. So let's do that. Applying this new definition, instead of integrating from 0, we're going to integrate from some number a that's positive. Everything else stays the same. We'll simply write this in a new notation, x to the negative 1/2, to make it easier to integrate, but that's equal to 1 over root x. And when we're done that integration step, we're going to let a approach 0. As a fussy little thing, we're going to have 0 go from the right. This rarely affects the calculations in any way, but it just means that a starts as a positive quantity and not, say, as a negative quantity straddling the problem point. So we're going to have a being positive heading down towards 0. All right, once we've applied that definition, we do exactly what we did with infinite quantities before. We evaluate the integral if we can. Here we add 1 to the power. We get x to the positive 1/2 over 1/2 between 1 and a. Then we sub in. We're going to have the half is really a 2 multiplier. We're going to plug in the 1 first, so we have 1 to the 1/2 minus a to the 1/2. And then we can look carefully at this expression, and as a goes to 0, a to the 1/2, which is just the square root of a, I can take the square root of 0, there's no problem there at all. That approaches 0 as well. So that term goes away, and we simply end up with 2. So this integral converges, and it converges to the finite value 2. Even though the integrand shoots off to infinity, the area underneath this curve on that interval can be represented as a finite value 2. Of course, not every example works out to a convergent integral. Let's take a look at this example here. The integral from 0 to 1 of 1 over x cubed also is improper for exactly the same reasons. We usually focus on nice simple powers because they illustrate all the properties that we want without overly complicating the integration step. But 1 over x cubed has the same asymptote horizontally, asymptote vertically. We're going to do the same thing we just did. Recognize that if we cut off our integral and talk about the area underneath the graph between a and 1, that will be finite. And so then we can sneak up on this 0 problem point where the integrand would be undefined. We write that down as applying the definition. The integral up to 1 of 1 over x cubed, which we will rewrite, making it easier to integrate as a power there, x to the negative 3. And we replace our lower problem point, the 0 here, with an a, and then let a go to 0 from the right, a value that's positive and heading down towards 0 afterwards. We're ready to integrate now. We copy the limit down. That'll be the last thing that we apply. If we have x to the negative 3, we add 1 to the power, divide by the new power, evaluate that between 1 and a. Take the limit again. This is negative a half. This time we have 1 over 1 squared minus 1 over a squared, the negative power, sometimes easier to visualize or compute with if we write it as a denominator. And then we're done the integration. We're ready to assess what happens as a approaches 0. Well, as a approaches 0, a squared also approaches 0, but 1 over a squared is going to approach infinity, or that limit does not exist. If that's the case, then everything else here is finite. There's no cancellation. This limit diverges, or this limit does not exist. And so we would say the area underneath the curve represented by the integral 0 to 1 of 1 over x cubed dx diverges. It does not approach any finite quantity when we extend that boundary down towards 0. What we're aiming for here is a general understanding of why we have improper integrals. Like, what does it mean for an integral to be improper? That usually means some infinite quantity is involved. And then recognizing how to apply a limit, or how to split up that integral problem into a regular integral with just finite quantities and a limit that pushes the boundary towards the infinity problem, and being able to handle the calculation process that comes out of that definition. If you have that, then you've understood the goal, or the concepts that are underlying all of these improper integral calculations.